So this is definitely more on the technical side, and I do agree that doing things that are useful is very important. This talk actually did start with a project that is still trying to do something that I think is very useful, but as a programmer, I obviously get sidetracked into all these interesting technical problems. So when I needed a particular kind of data visualization, I was like, well, how do I do this? This sounds kind of hard. And the obvious answer, which is never right, is, oh, I'll write my own library for it. So this is a talk about this. And yeah, it's probably not the right answer, because it turns out that doing charts is really hard, but the talk isn't really going to be just about charts, but more about the sort of interesting design principles that are there. So I'm partly based at the University of Kent, where I do research and teach software engineering and human-computer interaction, and I still do a little bit of work with F# works on F# trainings and such things. So the motivation for this was this project where the goal was to make facts great again. So the idea is, what could we do to make factual data more interesting so that people care more about them and maybe engage more with facts than with other things that they might be engaging with. And the attempt was to create sort of more transparent data visualizations that give people more power to explore and play with things. So that's the sort of background. That's one thing that the talk is about. The other thing that the talk is about is how to do this in a functional way. So I'll be using F#, and that's sort of just the implementation language. I think the interesting part here is that it's trying to sort of find a new way of looking at an interesting and I think quite tricky domain. So you can get sort of specific ideas about data visualization from this, but I think what's more important is that there's going to be sort of general principles that apply elsewhere as well. So when you talk to someone who does functional programming research, their first question whenever they face anything is, what is this actually? And then they start writing some equations, and then they tell you, oh, this is easy, this is trivial, this is just a monoid in the category of endofunctors. Chart isn't a monoid in the category of endofunctors, as far as I know. So the first question is, what is it that I'm actually working with? And I started by looking around, and if you look at, for example, Google Charts, a popular library, what is a chart? Well, they just list this. They have this enormous list of things. On the left, you can't really see them. Things like bar chart, column chart, line chart, fine area chart, scatter chart, histogram. But if you look at histogram, it's really just bars. Then there's combo chart. What is this even? And the list goes on. So this is really saying, well, chart is one of these 25 things that we thought you might need. So that's kind of useful in practice, because often you really do need just one of those. But it doesn't give you more flexibility to do new things. And one of the sort of nice motivations for this work is what the journalists at New York Times are doing, and they're producing visualizations like this one. So this is showing the history of who won different Olympic medals, or what countries won what number of Olympic medals over the history of the Olympics. And it's a really nice visualization. I really like it because it sort of shows interesting things about the world as well. You can see the two gaps, that's the two world wars. You can see the sort of red peak in there, which is during the Cold War. So it is a beautiful visualization, but it's really none of the ones that Google defines. So maybe a chart is really just an SVG where you have lots of shapes and pixel coordinates, and you have to do all this work manually. So that wasn't a very satisfactory answer either. So there's this sort of very low-level answer, which is, well, you just have to, and that's what you can do with D3. And D3 is a nice library, has a lot of helpers, like you can do scaling with it. There's interpolate cool, which is probably just something that they added for this particular Olympics chart. But fundamentally, you just end up working with x and y coordinates in pixels. Okay, yeah, that's how programming is done, but it's not really easy. And Google Charts is, on the other hand, the sort of super high-level answer where you just say bars and lines, and you can do only 25 things that they define. It gets even worse. So another inspiration from New York Times is that they've been doing a lot of interactive data visualizations. I'm going to show you this one. I find it. So this is a data visualization, quite a few years old now, 2 years, 3 years, which looks at various statistics over the sort of Bush presidency and Obama's presidency. And the idea is they'll show you something like the unemployment rate, and they show you the data for the years when Bush was president, and then you're supposed to be sort of, you have to fill in the rest before they actually tell you the ground truth. So obviously, during Obama presidency, everything got better. So let's do unemployment down. And then you can see how we did. Actually, it was a bit tricky because that was the start of the financial crisis. So, and then what is this? Number of immigrants convicted of crimes, deported. Well, I bet this is going down. And again, it's not. So this, I think, is another nice example of a really powerful data visualization because you have to play with it, and it really makes you think about the problem. But again, it's not on the Google Charts list. So if you look at these examples, you sort of start thinking, well, what are all the different things that we're dealing with? There's projections, so you often specify things in years or unemployment rates, and this has to be mapped to pixels. There's shapes, there's areas and lines, but I don't want to write those in sort of pixel coordinates. There's composition, you can put multiple things together, and there might be some interactivity. So I'm going to show you one way, one F-sharp library that I've been using in some of my work, which is trying to sort of build charts in a more compositional, functional way. So first example is just going to be a basic chart, basic bar chart, and I've got some data here. So what I'm going to do is I'm going to create a column with categorical value, let's say USA, and the continuous value, let's say 10,000. And then I'm going to say, let's call this call, and then I have a helper that will render this. So this is creating one column, and if I actually just do this, it rendered this gray square. So it sort of created one column, except it fills the whole area. So this is a good start, but not very great chart. So let's do some more things. I've got some data on UK election results, where I have party, color, and the value in 2019 and value in 2020. Should be for loop. And then I'm going to generate a series or a list of columns with, this is the party name, and this is going to be the value, and this is generating a list. And one of my primitives is this shape.layered, which just takes everything you give it and puts it over in the same space. So if I do this, now you actually start seeing something that sort of is getting into the bar chart direction. We have different bars. They take the full space, but they're nicely laid out, and different parties have different area of the chart. And the other thing I'm going to need is set the color. So I can say fill color, and then use the column, and now I've colored all the different things with different colors. And I think the last thing I want to do I want to add some space between the bars. And again, there's a primitive for doing this, which takes 4 floats. So that's 0, 10, 0, 10. And then I apply this operation to this colored column. And now I have some spaces between them. And my last primitive, and this is very, very much sort of something that's only chart relevant, is adding axes. And you can add them on all the different sides. So I'm going to add them on the usual bottom and left. And now I've actually constructed a bar chart from pretty much scratch, from sort of basic building blocks. But with not a lot of coding, I think the really nice thing here is that you work with elements of this charting domain like axes, bars, and composing them together. One of the sort of most interesting things that's happening here automatically. So if you look at the code, right, I never had to write any sort of pixels or any even like relative percentage. I really always work with numbers from the domain of the data. So when I say column, I say this is categorical value, and that's the name of the party. When I say this is the continuous value, and that's the name, that's the number of representatives they have in the parliament. And it all ended up being this chart, which is actually rendered in pixels. So the key thing that this is doing is that it's sort of giving me a higher level abstraction for working in the sort of closer to the domain, which then gets mapped to the low level stuff. And there's 2 things here that are nice. One thing, which is that it automatically handles scaling. So I just specify I want a bar chart where the name is Liberal Democrats, and the number is, let's say, 450 or something. That would be nice, wouldn't it? And then it gets mapped to these pixels. So you have two kinds of scales. One is continuous, and that's just numbers from some number that's low to some number that's high, like 0 to 30. And then you also have categorical scales, where it's really just a list of strings, list of values like Liberal Democrats, Labor, Conservatives. And then the space gets partitioned between these, and every single of them defines some area where you can sort of go from left end to the right end. So in F#, there's this nice way of representing it. You just define an algebraic data type, and then you have so here I have 2 types. One represents a value, that's basically position in the chart, and the other is scale, which is representing the sort of the entire space. What is like this sort of, if I go all the way from left to right, what is in there? So a value can be continuous, and then it's just a number. Or it can be categorical, and then it's a name of this category, like labor, together with left end and right end, or sort of a ratio between the left end and the right end, because you can say, if I have this bar here, then this is all area allocated for conservatives, and here this point is 0 and this point is 1, so that you can uniquely identify points. And then a scale can be either continuous, where you say, well, this is just an area from, say, 0 to 400, or it can be categorical, and then it's an array of strings or list of strings, such as conservative, labor, and so on. So there's categorical and continuous scales, and the nice thing is that the library will do the layouting automatically. Then the second question is, what is a chart? Where, again, this is just an algebraic data type that lists all the different primitives. So a shape can be some operation that changes the visual style, a line, or some sort of filled area. And it gets more interesting when you get to things like axes and padding. The last operation is this layered operation, which just means a shape is something that's composed by multiple shapes. And you'll notice here that I'm never anywhere specifying x and y coordinates in pixels. There's some values in line and shape, but they're really just domain values. So this is where I put Liberal Democrats 400. Now, implementing this turns out to be quite tricky if you're as bad as geometric projections as I am. So one really valuable thing that you get in FSARP, which I've been using here quite a lot, is units of measure. So this is the idea that you can annotate type with something like a physical unit that it represents, and you can define a generic type shape which has two different units, Vx, Vy, and they represent the x and y units. So if you have a chart where x is in kilometers and y is in seconds, they'll have different types and you'll never mix them up. So you're never going to accidentally compose a chart that has kilometers and seconds with a chart that has miles and seconds. So that's one useful thing, and I'm really mentioning this just because this was the sort of key thing that helped me actually implement this. And it does get tricky when you, in charts, what you're basically composing is a projection from these values in the domain, like kilometers or members of parliament, to pixels. And you do that for both x and y coordinates. So one of the sort of interesting technical bits in this bit of code is this idea of projection, where you're projecting from units of the domain, Vx, Vy, to units of the visual screen, Ux, Ui, which will typically end up being pixels. And then one of the sort of nice things you'll find in the code base is this project function, which takes two scales that represent what's the sort of space of values for the x-axis and y-axis. It takes a value in those same units. It takes a projection that's been calculated before, and it applies the projection to transform the value from, say, members of parliament to pixels. So this is a really nice use of units of measure, which I think, if I didn't have this in the language, I would have just spent 4 more days trying to get the multiplications right. So one other thing I want to show you is more about the compositionality. So I complained about the combo chart in Google Charts because it lets you compose 2 arbitrary things that they just thought you might want to compose. So a nicer thing I can do here is and I'm going to use another example, which will be a line chart. So I do have a primitive for specifying line, and this just takes a list of values, and I have another data set which is exchange rate between dollar and pound around June 2016. Wonder why? So here I'm just taking the index as the x value and the actual exchange rate as the y value. And this is my line, and I'm going to render it. And again, you get very sort of raw chart with just the line taking the whole space. And let's say that I want to do a few more things with this. So I want to compose a couple of components here. One is going to be the line, and I'm going to make it black. So this is just another sort of transformation where I say make the line black. And then I want to render this. I'm going to add axes as well. And now with axes and with black color, I get something that looks a bit more like a chart. And the one more thing I want to add is to sort of highlight the bits of the chart that are before Brexit, highlight the parts of the chart that are after Brexit. And I happen to know, and this is a bit of a heck I had to calculate to make this easy. I happen to know that the first 16 values on the chart are before Brexit, and then everything is after Brexit. So what I want to do is basically draw a background, draw a sort of filled rectangle that highlights one part of the chart. And to do this, I can just say, draw a shape. And a shape has a list of corners, and it will fill the area that I define. And my left bottom corner will be x is a 0, and then y is going to be a value in this exchange rate. So here I have 1.3. I'm going to start a bit lower with just 1. The second corner will be on the right. So this is value x is a 16, and then exchange rate is still 1. And I need 2 more points. One is the upper right corner, which is 16th day, exchange rate 1.8, and then going back to the left, I have 0 and 1.8. So the way I'm defining this shape is by the sort of values in terms of the domain. And now I actually filled the area. So what happened here is that as the automatic scaling works, it actually used the values that I used for these corners of the rectangle. So now the line has been moved to the middle, just because I said I wanted from 1 to 1.8. And it all gets sort of laid out automatically, and sort of it figures out where things should go. So just to make this nicer, I've got some colors for it. So I'm going to set fill color of this shape, and this should end here. And I've got one more shape, which I'm just going to paste here, and that's the other part, which is just filling the complementary part of the chart. So now I've sort of nicely composed a chart from 2 different shapes, or 3 different shapes, 2 rectangles, and 1 line. And this is already something that is really hard to do in pretty much any charting library that's high level, because they'll have things like columns and lines, but they're very different kinds of charts. You can't easily put them together. Here it works because the shape is just identified by these categorical or continuous values. And that's something that's sort of in the domain of the chart. So it's like exchange rates and days. And I can do one more thing here, and that's add a title. And this is going to be another interesting example. This is a bit of code that defines a title, and I'm not really going to cover everything about this here. We'll just use it. If I only render the title, then you just have some text in the middle of the screen. So this is the definition of a title. And what I want to do now is to sort of align this with the chart. Now, if I just did layered of this and the title, then honestly, I haven't tried this, so I don't know what will happen, but it's definitely not going to be right. Okay, yeah, so what happened here is that the chart got squished into the left bottom corner. That's because the title defines some coordinate space. It just says this is axis from 0 to 100, and the title is in the middle. So now I'm joining 2 incompatible axes, and that doesn't work. But I do have a primitive for fixing this, where I can say, I can basically override the scale. So this means I'm going to redefine what's the sort of scale around this chart element. And I'm going to say, I'll type this and then explain what's going on. So here I'm saying the sort of part of the chart that is taken by, let's say, the title is on the x-axis is from 0 to 100, on the y-axis is from 0 to 10, and this is where the title is. And I'm going to do the same thing for the other part, but here I'm going to say this starts from 10 and it goes to 90. So now I've got plenty of errors here. I think some of it is just bad indentation. Some of it is missing parentheses, I think, or too many parentheses. Well, I do have a hack here. So this is what I was meaning to do, and how bad was it? Well, I think I was pretty close. I don't know, it must be some missing brackets. That's always the problem. So if I use the right brackets, then I need shape. And shape is just this with axes. And this is viz. Renaming things is another problem. Okay, so now what I'm doing is I'm saying, take this space that's available, and let's just pretend that the values are from 0 to 100 in both directions, and let's allocate the upper bit for the title and the bottom bit for the chart itself. And let's divide the whole space, and then there's these two virtual areas at the top and at the bottom. The virtual area at the top is taken by the title, and that was that's just the title in the middle. The bottom area is taken by this old constructed charts. And the sort of scales within those areas don't interact in any way. They're hidden and they're independent. So this is a way in which you can actually compose multiple charts together, and you can choose whether they share some scales or share some axes or not. If you wanted to have different, say, exchange rate for different currencies over time as rows, then they would share the x-axis because that's going to be time, but they'd all have independent y-axes. So this is another fancy primitive that actually lets you compose these different charts. And I think this is probably the bit that took me the most time to actually figure out how to do. So the idea here is that when you're composing things, you often need to define multiple different ways or multiple different sort of operations that adjust how the composition works. In this library, I have three things. I can just put charts over each other, sharing scales, but then sometimes you need various ways to sort of tweak how the scaling works, and such as just make it independent. And that's also possible if you define a few extra composition primitives. So what are the key points here? I think one of the key things here is that you really have to think about what's the domain. And if it's charts, then you want to talk about things like axes or shapes, but you don't want to necessarily talk about those in pixels, or you don't want to talk about axes as just sort of little lines, because that would be too tedious. You do want to also sort of represent the data in a sensible way. So I do want to write just labor or just sort of 1.8 as an exchange rate. I don't want to represent all these things in pixels. And you need multiple different ways of composing things, because charts can be sort of put together in various ways. And in F#, you can use units of measure because they're really helpful for actually being able to implement it. So the one more thing I want to cover is to show you a couple of interesting design patterns. I think I'll only have time for two. So the first thing I want to show you is we've done all this hard work to actually construct a title. And this is something that probably every chart should have. So it's kind of annoying that I have to do all this work manually every time I want to do it. But fortunately, the nice thing here is that I can define my own primitives. So I can say title, which will be a function that takes some title and some shape and just adds title to this shape. And I'll basically copy pretty much what I've done before, except that I'll use the actual title and the actual shape. And then if I go back, I can just take my chart and say, this is the title, and I need my string. So now I can construct title just by actually saying title, and I can use it for all my different charts. So if I wanted to add a title to my earlier line chart, then this was general elections 2020. And then I can't render this one. And I've built this little primitive for adding title, which is derived from all the other more basic building blocks, and I can use it just as I was using axes and everything else. And in fact, some of the primitives I've been showing you before as primitives, they're actually derived and composed from other things. So I think one really important idea here is when you think about it, you have to sort of pick the right bottom level, the lowest level, and then you can build up things from those different levels. So in my case, I was using these sort of shapes and compositions and categorical and continuous values as my baseline, but from that you can easily rebuild all these things that Google is giving you in a list, like bar charts, line charts. They're really easy to construct from those more basic primitives. And the more basic primitives are themselves, in this case, just rendered as SVG. And the way that works, I think, is another useful functional pattern, which is where it sort of goes through a series of transformations. So I construct this shape, which is a relatively high-level representation of what I mean, what the chart is. But then if you just said, now write a function that takes a shape and produces SVG, I would be completely lost because you have to do quite a lot of tricky calculations and walk over it multiple times and so on. So instead of doing this, it actually goes through a number of stages where you start with the shape, you annotate the shapes with what's the area that different subshapes cover, and then that's what I call scaled. Then I calculate this sort of areas of a subshape, what parts of the screen are they going to be projected onto. That adds some more information, and once you do these two steps, now it's actually quite easy to turn it into a final SVG. So it goes through this sort of processing pipeline, and I have different types at each step, and it's just sort of function that goes from here to here, and so on. And then you compose them, and that's it. And this is something that you'll see in really a large number of functional code bases. Pretty much all the compilers do the same thing, where they go through various stages. You go from source code to untyped AST to typed AST to binary. So this is a pattern that sort of, I think you can see this in a compiler, and you're like, well, yeah, I guess this is how compilers work. But it's something that happens to be really, really useful in pretty much any domain. And well, the last bit I wanted to do is to actually do it with some animation. So what I'm going to do is I'll take my bar chart, and let's see. So this is going to be a function to create bar chart, and this is what we've done so far, but I'm going to change it a little bit. So what I'm trying to do is to do an animation that will animate the bar chart from 2019 values to 2020 values. So I'm going to change this into a function that takes the data, and it just renders whatever data you give it. And this is going to be sort of 2019 to 2020. And I'm just going to return it. And I'm going to use this Elm-based, Elm-style architecture for it. So I'll need a render function. And I'll say more about what this is actually doing, where I'll just render the bar chart with some data. And to get the data, what I'm going to do to get the data is I'll iterate over all my election data and then return a value that's between the 2019 and 2020 values. So it's like linear transformation from one to the other. And the state that I'm passing here represents the sort of whether I'm showing 2019 or 2020 or something in the middle. So it's going to be 0 for 2019, 1 for 2020, 0.5 for a value that's sort of animation in the middle. And to get this to actually run, I need an update function that takes a state, takes an event, and returns a new state. I'll show this later. And my initial state is 0, so I start with the 2019 values, and then I forgot in which order this takes the arguments. So fortunately, if I click the right thing, and I have enough space, then I'll learn that the first thing is my render function, the second thing is my update function, no, the first thing is actually the state, and then this is it. Okay, so let's see if this actually renders something. It did render the same thing we had before, so that's a good start, but the title is updated. And now I want to do some actual animating. So I'll need a button to start my animation, and I'll just generate a div element here, followed by a button, and then the button is going to be text, show 2020, and now I need some events. So I'm going to define a type for events, and event can be I want to start the animation, or I want to make a step of the animation. And when you click on the button, we're just going to trigger the start event, so the button will start the animation. And that's it. And now in my update function, I'll have a look at the event, and if this is start, then I'll just return some smaller, higher number, because I want to iterate from 0 to 1. And if this is animate, then I'm going to take whatever state I've got so far, and I'll increment it by a little bit. So right now, if I save it, does it actually render correctly? I have some error here. Where's my error? My render is wrong. Trigger, this needs a function here. So this is an event handler. Well, so now if I click on it, you probably don't see it, but the red goes a little bit down, a very, very tiny bit. So it made one step of the animation, and then the last bit I need to actually make it work is to say, if the state is between 0 and 1, which means I've already started animating, then set a timeout so that it does the next animate step after 10 milliseconds. And now, if I save it, I get no error. If I click show, now it's showing data for 2019. I click, and it goes to 2020. This didn't actually look that great because it was automatically rescaling. So the blue was always 100%. I don't like that. I can fix this by going here and saying, let's fix the scale of this. the X scale I let automatic, but for the Y scale, we're going to override that. And what do I need to give this? This needs the lower value, which is 0, and upper value, which is going to be, let's say, 400. And now that scale is fixed, so if I do the animation, blue actually goes up. So the powerful idea here is that you have these states, and they get transformed by updates. And in the Elmish architecture, you just render each state. So that's pretty much all I wanted to cover. So really, I've been talking about charts because I think that was an interesting, tricky domain. But the fundamental question was, what is this thing that we're working with? And with functional languages, you have great tools for expressing the domain in sort of high-level, composable way. And in F#, it's easy to implement because we have beautiful units of measure and beautiful Fable compiler for turning things in JavaScript and beautiful Ionite editor for actually writing the code. Thank you.